Currently, U.S. fighters rely on the AIM-120 AMRAAM. The AIM-174B was introduced as a stopgap measure by adapting the SM-6 for air-to-air use. This confirms it is designed for stealth carriage. The Navy has not released a specific range figure. Any precise numbers circulating online are speculative. The program is still in the flight testing phase. It is not yet an operational weapon deployed to squadrons. The AIM-424 is specifically designed to counter this aircraft. Its primary long-range weapon is the PL-15 missile. This missile has a reported range of 200 to 300 kilometers. This allows the J-20 to carry up to 6 of these missiles internally. Such capability significantly increases its lethality. The PL-15 missile is a primary threat to U.S. air superiority. The race for dominance in the skies is accelerating faster than ever before. Engineers on both sides push materials and propulsion to absolute limits. Every pound of weight saved inside a stealth bay counts toward survival. Naval strategists map out scenarios where seconds decide the fate of an entire carrier strike group. The stakes in modern aerial warfare leave zero margin for tactical error. Pilots flying miles away from any visual contact rely entirely on onboard sensors. A fraction of a second in reaction time can mean the difference between victory and catastrophe. Defense contractors work under strict secrecy to deliver prototypes on aggressive timelines. Testing ranges in remote deserts record high-speed telemetry under watchful eyes. Data streams flow back to control rooms where engineers analyze every anomaly. The physics of max speed interception demand unprecedented thermal and structural endurance. Flight control systems undergo rigorous software updates after every single test flight. Ground crews inspect composite airframes for microfractures caused by extreme atmospheric friction. Commanders review these test results to determine operational readiness milestones. Logistics networks prepare for the eventual integration of the new missile into active squadrons. Maintenance personnel will soon need specialized training for handling advanced propulsion systems. Shipboard armory bays require reconfiguration to safely store larger next-generation munitions. Tactical doctrines shift to accommodate weapons that strike far beyond the horizon. Adversaries continuously upgrade their electronic countermeasures to blind incoming seekers. Frequency-hopping radars and decoy flares add layers of complexity to target acquisition. Thermal signature reduction remains a top priority for stealth platform designers. Engine exhaust suppression systems hide fighter jets from infrared tracking sensors. Aerodynamic profiles are constantly refined to maximize lift without compromising radar stealth. Wind tunnel tests simulate extreme angle of attack maneuvers at supersonic speeds. Aviators train in advanced flight simulators to master beyond visual range engagement protocols. Decision-making cycles must adapt to the blistering speed of modern missile combat. Command structures evaluate decentralized launch authorization for fast-moving engagements. Intelligence analysts monitor foreign production lines for signs of unexpected technological breakthroughs. Satellite imagery tracks the expansion of strategic air bases across contested regions. Diplomatic channels address escalating tensions fueled by rapid military modernization. Defense budgets reflect the massive financial commitment required to maintain technological superiority. Taxpayers fund these multi-billion-dollar programs in the name of national defense. Military historians draw parallels to past arms races that reshaped global power dynamics. Strategic deterrence relies on convincing potential rivals that aggression carries an unacceptable price. The ultimate goal of these weapons is to ensure they never actually have to be fired in anger. Peace through strength remains the guiding principle behind American defense policy. As testing continues, all eyes remain focused on the desert skies where the future of combat is being forged. The next milestone in the program will reveal whether early performance promises hold true. Industry observers eagerly await official confirmation of speed and range specifications. Until then, development proceeds behind heavily guarded gates and classified networks. The outcome of this technological race will define air dominance for generations to come. America's new secret killer missile prepares to step out of the shadows. The balance of power in the skies hangs in the balance. Engineering a hypersonic missile means building systems that survive environments where traditional materials simply melt away. Calculating how extreme heat and rushing air interact at thousands of miles an hour pushes modern computers to their limits. Engineers must predict aerodynamic pressures and surface temperatures down to the last fraction of a degree before anything ever touches the sky. Without exact thermal protection models, the extreme friction of flight would tear the airframe apart in seconds. Designers often rely on reactive modeling modes, where fluid dynamics solutions must be painstakingly extracted and validated to guarantee reliability. Support anti-ship ballistic missiles. Campaign. Use. To survive these brutal velocities, engineers now look to low-temperature plasma as a critical enabling technology for hypersonic flight. Harnessing this ionized gas offers a way to control airflow and propulsion when ordinary control surfaces fail. Yet moving from these physical breakthroughs to a reliable weapon brings a whole separate layer of digital complexity. Engineers increasingly rely on virtual models to optimize complex engineering systems before building physical prototypes. By blinding enemy radar, infrared sensors, and satellite networks, fleets can disrupt targeting before attacks begin. Cold War history shows that mixing electronic jamming with tactical tricks is the best way to neutralize hostile surveillance. Swarming tactics are reshaping combat across land, sea, and air as distributed units replace rigid command hierarchies. This shift drives modern drone warfare toward higher autonomy and seamless manned-unmanned teaming. Real-world conflicts prove these anti-access zones often fall far short of their terrifying paper capabilities. That is why pairing physical countermeasures with electronic disruption guarantees freedom of movement for the fleet. Malice arrives to break open those bubbles and restore dominance. The secret killer is finally ready to rewrite the rules of the sky.